In this video, we'll walk through 30 step-by-step Exam 1 problems together. Get your calculator out and let's get started. We have a chemist dissolves 2.345 grams of an unknown solid in water and fills a 25 milliliter volumetric flask. What is the concentration in grams per liter and moles per liter if the molar mass is 142.2 grams per mole? This problem will be more like a puzzle of putting together units in the correct places. We need grams and liters to divide them to make grams per liter. We have grams, but we need liters. Milliliters is a prefix unit, and we can convert to the base unit liters using the conversion factor 1,000 milliliters per every 1 liter. Setting up units to cancel, I will start with 25 milliliters over 1. In the next fraction, I can put 1,000 milliliters on the bottom and 1 liter on the top. Milliliters cancel out and I am left with liters. Dividing the values, we get 0.02500 liters. Now we have grams and liters, so we can divide 2.345 grams and 0.02500 liters to make the new derived unit grams per liter. We get 93.80 grams per liter. Now we can work on converting the units to moles per liter. We have liters on the bottom already, but we need to convert grams to moles, and they gave us the molar mass that combines grams and moles together. This is a good sign that we can use the conversion factor to cancel out the unit we already have to get to the unit we need. Setting up units to cancel, I will start with 93.8 grams on the top and 1 liter on the bottom so we can have a top and bottom fraction. In the next fraction, I will put 142.2 grams on the bottom and 1 mole on the top. Grams cancel out and we are left with moles per liter. Dividing the values, we get 0.6596 moles per liter. We now have our two concentration units needed, 93.80 grams per liter and 0.6596 moles per liter. Rank the following measurements in terms of increasing precision: 2.1 grams, 2.100 grams, 2.10 grams. Explain your reasoning using significant figures. The precision of a measurement is indicated by the number of significant figures it contains. More significant figures means a value is more precise, and the most precise measurement will have the greatest number of significant figures. 2.1 grams has 2 significant figures. 2.10 has 3 significant figures. 2.100 has 4 significant figures. Based on the number of significant figures, the order from least precise to most precise is 2.1, 2.10, and then 2.100. A 1.50 milliliter sample of mercury has a mass of 20.3 grams. Determine the density in grams per milliliter and kilograms per meter cubed. This problem will be more like a puzzle as well. They are asking for grams per milliliter, and we are given grams and milliliters so we can divide them with grams on the top and milliliters on the bottom to create the new derived unit grams per milliliter. 20.3 grams divided by 1.50 milliliters will be 13.5 grams per milliliter. Now we need to convert grams to kilograms and milliliters to cubic meters. Cubic meters may look strange, but any unit cubed is really a volume measurement as well. Grams to kilograms is a base to prefix conversion, so we can use 1,000 grams for every 1 kilogram, and for milliliters to cubic meters, we have to know that 1 milliliter is equal to 1 cubic centimeter. We can then connect cubic centimeters to cubic meters because it will be a prefix to base unit conversion too. It's just cubed. There are 100 centimeters in 1 meter, and to make it a cubic conversion, we will cube both top and bottom of the conversion factor so it will match cubic meters and cubic centimeters. Setting up all units to cancel, we start with 13.5 grams over 1 milliliter. We can start with grams or milliliters first, but I will start with grams to cancel out units. In the next fraction, 1,000 grams goes on the bottom and 1 kilogram on the top. In the next fraction, 1 cubic centimeter goes on the bottom and 1 milliliter on the top. In the next fraction, 1 cubic meter goes on the bottom and 100 cube centimeter cubed on the top. Grams cancel out, milliliters cancel out, and cubic centimeters cancel out, leaving us with kilograms on the top and cubic meters on the bottom. Multiplying and dividing all values, we get 1.35 times 10 to the 4th kilograms per cubic meter. We now have both density conversions, 13.5 grams per milliliter and 1.35 times 10 to the 4th kilograms per meter cubed. Convert 0.0750 meters cubed to microliters. This conversion has volume due to the liter and the cubic unit. To connect the two, we can use 1 cubic centimeter is equal to 1 milliliter. Cubic meters is closest to cubic centimeters because we know that we can convert meters to centimeters with a base to prefix conversion using 100 centimeters for every 1 meter, and then we can cube the conversion factor to make it cubic meters and cubic centimeters. Setting up the unit map, we can write cubic meters to cubic centimeters and 100 cubed centimeters cubed over 1 meter cubed. Next, we can connect cubic centimeters to milliliters because there is 1 cubic centimeter per 1 milliliter. Milliliters to microliters will be a prefix to prefix conversion where we convert to the base unit liters in between. There are 1,000 milliliters in 1 liter and 1 times 10 to the 6 microliters in 1 liter. Setting up all units to cancel, we start with 0.0750 cubic meters over 1. In the next fraction, 1 cubic meter goes on the bottom and 100 cubed centimeters cubed on the top. In the next fraction, 1 cubic centimeter goes on the bottom and 1 milliliter on the top. In the next fraction, 1,000 milliliters goes on the bottom and 1 liter on the top. In the next fraction, 1 liter goes on the bottom and 1 times 10 to the 6 microliters on the top. Cubic meters cancel out, cubic centimeters cancel out, milliliters cancel out, liters cancel out, and we are left with microliters. Multiplying and dividing all values, we get 7.5 times 10 to the 7th microliters. An atom has a mass number of 81 and 35 protons. Write the full chemical symbol and determine the number of electrons for the 2- ion. The chemical symbol will have the mass number at the top left, the atomic number at the bottom left, the element symbol, and then the charge at the top right. Mass number is protons plus neutrons, and the atomic number is the number of protons and is also the identity of the element that can be found on the periodic table. Charge is equal to protons minus electrons, and only the electrons will change with charge. 81 goes at the top left, 35 at the bottom left, and from the periodic table, 35 is the atomic number for bromine, so Br will be our element symbol. The charge at the top right will be -2, and to find the number of electrons, we can use the charge equation, -2 equals 35 protons minus x. Adding x to the other side and then adding 2 to 35, we get 37 electrons. Calculate the average atomic mass of boron given 80.1% B11 and 19.9% B10. To calculate the average atomic mass, we will first change the percent abundance values to decimals by dividing by 100, multiply the decimal by the individual mass for that isotope, and then add all values together from step 2. Average atomic mass is the weighted average, so we take the percents of each isotope mass and add them together. 80.1% and 19.9% will become 0.801 and 0.199. Multiplying each decimal by their individual isotope mass, we get 8.811 and 1.99. Adding those values together, our average atomic mass for boron will be 10.801 AMU. They can also ask questions giving you the average atomic mass, the two isotopes' individual masses, and then asking which is the most abundant, and the isotope mass that is closest to the average atomic mass will always have the highest percent abundance. Here, B11 is 80.1% of the weighted average, and we can see that our average atomic mass is closest to 11. Determine the formula of a compound that contains 50.8% barium, 13.7% sulfur, and 27.5% oxygen by mass. When given percentages for each element, we are going to find the empirical formula. Empirical formula is the lowest whole number ratio that we can have for all elements. To find the empirical formula, we will assume that we have a 100-gram sample, and this means that we change the percents to grams for each element. We're not going to actually change the values because if we have 100%, that can also be 100 grams. For example, 12% carbon becomes 12 grams of carbon. We then convert grams to moles for each element by dividing by the molar mass. With all the mole values found, we will divide each by the lowest number of moles to have all whole number ratios for our empirical formula. If we do not have all whole numbers in this step, we multiply all values by the same number to get all whole numbers. Here are the common decimals you can find in this step and what value to multiply it by to get a whole number. If you have a decimal around 0.14, multiply by 7, 0.25, multiply by 4, 0.33, multiply by 3, 0.5, multiply by 2, 0.66, multiply by 3, and 0.75, multiply by 4. Using the steps to solve the problem, we start with 58.8 grams of Ba, 13.7 grams of sulfur, and 27.5 grams of oxygen all over 1 so we can convert to moles. Using the molar mass for each, we will convert each element to moles. In the first fraction, 137.33 grams of barium goes on the bottom and 1 mole of barium on the top. We will do the same for the other two elements with their molar masses and calculate. We get the moles for each element, and we want to have a whole number at the end without any rounding, so I just write down all decimals to make sure I get an exact number at the end. The moles of sulfur is the lowest mole amount found, so I will divide each value by moles of sulfur to get the whole number ratios we need for the empirical formula. We don't want to do any rounding, so we need numbers with decimals like 0.99, 0.01, or 0.00 to know we did the problem correctly. If not, we can look at the decimal chart and what to multiply it by to get a whole number, or we messed up in a calculation somewhere. Dividing each by moles of sulfur, we get 1.00 barium, which will round to 1 Ba, 1 sulfur, and 4.02 oxygen, which will round to 4 oxygens. Present the elements in the empirical formula in the order the problem gave them in. The empirical formula will be BaSO4. Name and write formulas for all binary compounds formed between aluminum and elements in group 17. Binary compounds are made of two elements. We will use group 17, the halogens, and create ionic compounds with aluminum. These will be ionic compounds because aluminum is a metal and the halogens are all nonmetals. To write the formulas for the ionic compounds, we use their charges from the periodic table and cross them. Aluminum has a +3 charge and all halogens will have a -1 charge. Going down the group for the halogens, we can create AlF3, AlCl3, AlBr3, and AlI3. For the names, we just have to write the name of the metal, and then for the nonmetals, change the ending to IDE. The names will be aluminum fluoride, aluminum chloride, aluminum bromide, and aluminum iodide. Balance this reaction. H₃PO₄ plus CaOH2 creates CaCl3PO₄ plus H₂O. To balance, I will start with the first element in the first compound. If it only appears once on each side, it is a good element to start with. Hydrogen appears in multiple places, not once on each side, so we will save it for later. I will move to the next element, scanning left to right. P is the next element, but PO4 stays together on both sides, so we can balance it as 1. On the left, we have 1 PO4, and on the right, we have 2 PO4. I can put a 2 in front of H₃PO₄ to have 2 PO4s on both sides. Scanning left to right, the next element is Ca. Ca appears once on each side, so it'll be a good element to balance next. On the left, we have 1 Ca, and on the right, we have 3 Cas. I can put a 3 in front of CaOH2 to have 3 Cas on both sides. The last two elements to balance are O and H. H is in one less compound, so it will be a little easier to balance than oxygen. Counting all the hydrogens on the left, we have 6 coming from 2H₃PO₄ and 6 coming from 3CaOH2 to make 12 hydrogens total. I can put a 6 in front of H₂O to make 12 hydrogens total on the right side. The last element is oxygen. On the left side, we have 8 oxygens from 2H₃PO₄ and 6 oxygens from 3CaOH2 to make 14 total on the left side. On the right side, we have 8 oxygens coming from Ca₃PO₄ and 6 oxygens coming from 6H₂O to make 14 oxygens on the right side. Oxygen is balanced as well. We can recheck all elements. We have 12 H's on each side, 2 P's on each side, 14 O's on each side, and 3 Ca's on each side. The equation is balanced. How many formula units are in 4 grams of CaNO₃? Moles is the middle ground for conversion, so in our unit map, we can first convert from grams of calcium nitrate to moles of calcium nitrate to formula units of calcium nitrate. To convert from grams to moles, we'll use the molar mass for calcium nitrate. To calculate the molar mass, we will add together 1 Ca, 2 N's, and 6 O's to get a total of 164.1 grams per mole. To convert from moles to formula units, we'll use Avogadro's number, and the conversion factor will be 6.022 times 10 to the 23rd formula units of CaNO₃ per every 1 mole of CaNO₃. Setting up all units to cancel, we start with 4 grams of CaNO₃ over 1. In the next fraction, 164.1 grams of CaNO₃ goes on the bottom, and 1 mole of CaNO₃ on the top. In the next fraction, 1 mole of CaNO₃ goes on the bottom, and 6.022 times 10 to the 23rd formula units of CaNO₃ on the top. Making sure all units cancel, we have grams of CaNO₃ cancel, moles of CaNO₃ cancel, and we are left with formula units of CaNO₃. Multiplying and dividing all values, we get 1.47 times 10 to the 22nd formula units of CaNO₃. A 1.5 gram sample of magnesium reacts with excess HCl. How many liters of H2 gas are formed at STP? The problem mentions a reaction, so we first have to write the balanced chemical equation. The wording will tell us what our reactants and what our products will be. Mg reacts with HCl will tell us that Mg and HCl are reactants. H2 is formed, but all elements have to be on the reactants and product side, so we are missing a product. When an element in a compound reacts, this will be a single replacement reaction where the element replaces one of the elements in the compound that has the same charge, positive or negative. Mg has a positive charge and will replace hydrogen that also has a positive charge. Mg will bond with Cl, and crossing the charges we get MgCl2 as our other product. Balancing the equation, we need 2 HCl. For any single replacement reaction, we should also check the activity series to make sure the element replacing the other in the compound is higher on the activity series. This tells us that the element is more reactive and the reaction can occur. Mg is higher than H2 on the activity series, so the reaction will occur and we can continue. Let's write down what they gave us to start with and what they are asking us to find. We are given grams of magnesium and we need to find liters of H2. We need to convert to a new identity, H2, and to do this, we need to be in moles of Mg to use the mole-to-mole ratio to convert to moles of H2. We have grams of Mg right now, so we need to use the molar mass of Mg to convert to moles of Mg. The molar mass for Mg is 24.31 grams of Mg per every 1 mole of Mg. After that, we can use the mole-to-mole ratio using the coefficients from the balanced chemical equation to convert to moles of H2. In the equation, we have 1 Mg and 1 H2, so the mole-to-mole ratio will be 1 mole of Mg for every 1 mole of H2. To convert from moles of H2 to liters of H2, we can use the STP conversion, 22.4 liters per every 1 mole. For the STP conversion, the compound is H2 when we are converting from moles H2 to liters H2, so the whole conversion factor is 22.4 liters of H2 for every 1 mole of H2. Remember, every conversion should have a number, a unit, and a compound. Setting up all units to cancel, we start with 1.5 grams of Mg over 1. In the next fraction, 24.31 grams of Mg goes on the bottom and 1 mole of Mg on the top. In the next fraction, 1 mole of Mg goes on the bottom and 1 mole of H2 on the top. In the next fraction, 1 mole of H2 goes on the bottom and 22.4 liters H2 on the top. Making sure all units cancel, grams of Mg cancel out, moles of Mg cancel out, moles of H2 cancel out, and we are left with liters of H2. Multiplying and dividing all values, we get 1.38 liters of H2. A compound is 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen. Its molar mass is about 88 grams per mole. Find the empirical and molecular formulas. We are going to use the percentages given for each element to first find the empirical formula. Afterwards, we can use the molar mass given to find the molecular formula. Using the steps to solve the problem, we start with 54.5 grams of carbon, 9.1 grams of hydrogen, and 36.4 grams of oxygen all over 1 so we can convert to moles. Using the molar mass for each, we'll convert each element to moles. In the first fraction, 12.01 grams of carbon goes on the bottom and 1 mole of carbon on the top. We will do the same for the other 2 elements with their molar masses and calculate. We get the moles for each element, and we want to have a whole number at the end without any rounding, so I just write down all decimals to make sure I get an exact number at the end. The moles of oxygen is the lowest mole amount found, so I will divide each value by moles of oxygen to get the whole number ratios we need for the empirical formula. We don't want to do any rounding, so we need numbers with decimals like 0.99 and 0.01 or 0.00 to know we did the problem correctly. If not, we can look at the decimal chart and what to multiply by to get a whole number. Dividing each by moles of oxygen, we get 1.99 carbon, which will round to 2 carbon, 3.96 hydrogen, which will round to 4 hydrogen, and 1 oxygen. The empirical formula will be C2H4O. To find the molecular formula from the empirical formula, we will first calculate the empirical formula's molar mass, then we will divide the molecular formula's molar mass, by the empirical formula's molar mass. The molecular formula's molar mass will always be given in the problem and will just say molar mass or molecular mass. When we divide the molecular formula's molar mass by the empirical formula's molar mass, we find the number of units to multiply the empirical formula by to get the molecular formula. The number of units should be a whole number. Step 3 is multiply the number of units by the empirical formula to get the molecular formula. Using the steps, we will first find the empirical formula's molar mass. 2 carbons, 4 hydrogens, and 1 oxygen will give us 44.06 grams per mole for the empirical formula. Dividing 88, the molecular formula's molar mass, by 44, we get 1.99, which will round to 2 units. We now multiply the number of units by the empirical formula to get the molecular formula. We multiply each element in the empirical formula to get C4H8O2. Our molecular formula is C4H8O2. A solution of Na₂SO₄ is prepared by dissolving 5 grams in 250 milliliters of solution. Calculate the molarity of Na+ ions. Molarity has units of moles of solute divided by liters of solution. For the molarity of Na+ ions, the units will be moles Na+ divided by liters of solution. We need to find moles of Na+ and liters of solution. Let's first find moles of Na+ from the grams of Na₂SO₄ given. Setting up our unit map, we can start with 5 grams of Na₂SO₄, convert to moles of Na₂SO₄, and then moles of Na+. To convert from grams of Na₂SO₄ to moles of Na₂SO₄, we use the molar mass of Na₂SO₄. To convert from moles of Na₂SO₄ to moles of Na+, we can use a mole-to-mole ratio by counting how many Nas we have in the compound. We have 2 Nas in one compound, so the mole ratio will be 2 moles of Na+ ions for every 1 mole of Na₂SO₄. Setting up all units to cancel, we start with 5 grams of Na₂SO₄ over 1. In the next fraction, we put 142.04 grams of Na₂SO₄ on the bottom and 1 mole of Na₂SO₄ on the top. In the next fraction, we put 1 mole of Na₂SO₄ on the bottom and 2 moles of Na+ on the top. Grams of Na₂SO₄ cancel out and moles of Na₂SO₄ cancel out, leaving us with moles of Na+. Multiplying and dividing all values, we get 0.0704 moles of Na+. Next, we can find liters of solution. Setting up our unit map, we can start with 250 milliliters of solution and convert to liters of solution. To convert from milliliters to liters, we can use a prefix to base unit conversion. The conversion factor will be 1,000 milliliters of solution for every 1 liter of solution. Setting up all units to cancel, we start with 250 milliliters of solution over 1. In the next fraction, we put 1,000 milliliters of solution on the bottom and 1 liter of solution on the top. Milliliters of solution cancel out and we are left with liters of solution. Dividing the values, we get 0.2500 liters of solution. We have moles of Na+ and liters of solution, so we can now divide these two values to get molarity of Na+. 0.0704 moles of Na+ divided by 0.2500 liters of solution will give us 0.282 molar Na+. A student obtained a yield of 4.52 grams from a reaction with a theoretical yield of 6.75 grams. Calculate the percent yield. To calculate the percent yield, the equation is actual yield divided by theoretical yield times 100. The actual yield is 4.52 grams and the theoretical yield is 6.75 grams. 4.52 divided by 6.75 times 100 will be a percent yield of 67.0%. Identify which compounds are strong electrolytes. HNO3, BaOH2, CH3COOH, and C6H12O6. Strong electrolytes will be soluble ionic compounds, strong acids, and strong bases. The strong acids that we have to memorize are HCl, HBr, HI, HNO3, HClO3, HClO4, and H₂SO₄. Strong bases that we have to memorize are LiOH, KOH, NaOH, RbOH, CSOH, CaOH2, SrOH2, and BaOH2. HNO3 and BaOH2 are strong acids and bases, so they will both be strong electrolytes. CH3COOH is a weak acid and would be a weak electrolyte. C6H12O6 is a covalent compound and would be a non-electrolyte. Determine the mass of Fe₂O₃ that can be produced from 10 grams of Fe and XSO2. The question mentions a reaction, so we first have to write the balanced chemical equation. Produced from Fe and O2 means that Fe and O2 are the reactants, and Fe₂O₃ is the product. To balance, we need a 2 in front of Fe₂O₃, a 3 in front of O2, and a 4 in front of Fe. We are given 10 grams of Fe, and we are asked to find grams of Fe₂O₃. We have to convert to a new compound, and to do this, we need to be in moles of Fe to use the mole-to-mole ratio from the balanced chemical equation to convert to moles of Fe₂O₃. To convert from grams to moles of Fe and moles to grams of Fe₂O₃, we have to use the molar mass for each. The molar mass for Fe will be 55.85 grams of Fe for every 1 mole of Fe. The mole ratio will be 4 moles of Fe for every 2 moles of Fe₂O₃. The molar mass for Fe₂O₃ will be 159.7 grams of Fe₂O₃ for every 1 mole of Fe₂O₃. Setting up all units to cancel, we start with 10 grams of Fe over 1. In the next fraction, 55.85 grams of Fe goes on the bottom and 1 mole of Fe on the top. In the next fraction, 4 moles of Fe goes on the bottom and 2 moles of Fe₂O₃ goes on the top. In the next fraction, 1 mole of Fe₂O₃ goes on the bottom and 159.7 grams of Fe₂O₃ goes on the top. Grams of Fe cancel, moles of Fe cancel, moles of Fe₂O₃ cancel, and we are left with grams of Fe₂O₃. Multiplying and dividing all values, we get 14.3 grams of Fe₂O₃. A compound contains 8 grams of carbon and 2 grams of hydrogen. What is the empirical formula? We are going to use the grams given for each element to find the empirical formula. Using the steps to solve for the empirical formula, we start with 8 grams of carbon and 2 grams of hydrogen all over 1, so we can convert to moles. Using the molar mass for each, we will convert each element to moles. In the first fraction, 12.01 grams of carbon goes on the bottom and 1 mole of carbon on the top. In the second fraction, 1.01 grams of hydrogen goes on the bottom and 1 mole of hydrogen on the top. We get the moles for each element, and we want to have a whole number at the end without any rounding, so I just write down all decimals to make sure I get an exact number at the end. The moles of carbon will be the lowest mole amount found, so I will divide each value by moles of carbon to get the whole number ratios we need for the empirical formula. Dividing each by moles of carbon, we get 1 carbon and 2.97 hydrogen, which will round to 3 hydrogens. The empirical formula will be CH3. Determine the number of neutrons in a sample of oxygen 16. We are given an element and its mass number. Mass number is equal to protons plus neutrons, so we can find the number of protons to subtract. We can find the atomic number for oxygen on the periodic table. Oxygen has an atomic number of 8 and will have 8 protons. 16 minus 8 equals 8 neutrons. How many moles of precipitate form when 50 milliliters of 0.100 molar BaCl2 is mixed with 50 milliliters of 0.100 molar Na₂SO₄? When two compounds are mixed together, this will be a double replacement reaction. When a precipitate is mentioned, this is a special type of double replacement reaction called a precipitation reaction. A precipitation reaction will form a precipitate, a solid or an insoluble product based on solubility rules. We will write the balanced chemical equation and find the precipitate, and this will be the compound we have to solve for. BaCl2 and Na₂SO₄ are our reactants because they are initially mixed together. For a double replacement reaction, first write the charges for each element in the compounds, and then the positively charged ions will bond with the negatively charged ions of the other compound. Ba has a +2 charge, Cl has a -1 charge, Na has a +1 charge, and SO4 has a 2- charge. The positively charged Ba2+ will bond with the negatively charged SO4 2-. The positively charged Na+ will bond with the negatively charged Cl-. Crossing charges, Ba2+ and SO4 2- will create BaSO4 because the 2's cancel out. Na+ and Cl- will create NaCl. Looking at solubility rules, we have all sulfates are soluble except bonded to calcium, strontium, barium, mercury, lead-2, and silver. Barium is one of the exceptions, so BaSO4 is insoluble and is a solid. All other compounds will be aqueous, so we write AQ for the state of matter. To balance the equation, we need 2 NaCl. Before starting the conversion, molarity is best written separately as moles per liter for each compound, so we can see what units we can cancel out. 0.1 molar BaCl2 will be 0.1 moles of BaCl2 for every 1 liter of BaCl2, and the same for Na₂SO₄. It is best to start with the compound we are given the most information for, but for this problem, we are given the same amount of information for both reactants. Whenever we are given values for more than one reactant, this is a limiting reactant problem. One of these reactants is going to run out first and limit the reaction, so to find the limiting reactant, the goal is to convert both reactants to the same unit of product. The smaller amount of products found will be the answer and will be called the theoretical yield and will come from the limiting reactant. The larger product amount found will never be made because the reaction stops at the smaller amount, so just cross it out so it's not confusing. We need to find moles of BaSO4 for the answer so we can convert both reactants to moles of BaSO4, and the smaller amount made will be the answer. To convert milliliters of BaCl2 to moles of BaSO4, we have to use the mole-to-mole ratio from the equation to convert to the new compound. We have the molarity of BaCl2 that connects moles of BaCl2 and liters of BaCl2 together, so we can convert milliliters of BaCl2 to liters of BaCl2 to be able to use the molarity to convert to moles of BaCl2. Milliliters to liters of BaCl2 will be 1,000 milliliters for every 1 liter. We will then use the molarity as the next conversion factor. We have moles of BaCl2, so we can use the mole-to-mole ratio from the equation to convert to moles of BaSO4. The mole-to-mole ratio will be 1 mole of BaCl2 for every 1 mole of BaSO4. The unit map for Na₂SO₄ will be the same. We can set up both starting values to start canceling out units. We write 50 milliliters of BaCl2 over 1. In the next fraction, 1,000 milliliters goes on the bottom and 1 liter on the top. In the next fraction, 1 liter BaCl2 goes on the bottom and 0.1 moles BaCl2 on the top. In the next fraction, 1 mole of BaCl2 goes on the bottom and 1 mole of BaSO4 on the top. We set up the conversion factors for Na₂SO4 as well and make sure all units cancel out. For both, we are left with moles of BaSO4, so we can multiply and divide all values to see if we have a limiting reactant. For both, we get 0.005 moles of BaSO4. This is a special problem because we don't have a smaller number, so this means that both reactants run out at the same time. For every problem that has more than one reactant, we still want to treat it as a limiting reactant problem just in case. The answer will be 0.005 moles of BaSO4. Write the complete ionic and net ionic equation for the reaction of PbNO₃2 and Ki. When two compounds are mixed together, this will be a double replacement reaction. We will write the balanced chemical equation and then find the states of matter for all compounds to make sure that a new state of matter has been created. If a new state of matter has not been created for a double replacement reaction, there will be no reaction. PbNO₃2 and Ki are our reactants. For a double replacement reaction, first write the charges for each element in the compounds, and then the positively charged ions will bond with the negatively charged ions of the other compound. Pb has a +2 charge, NO3 has a -1 charge, K has a +1 charge, and I has a -1 charge. The positively charged Pb2+ will bond with the negatively charged I-. The positively charged K+ will bond with the negatively charged NO3-. Crossing charges Pb2+ and I- will create Pbi2, K+ and NO3- will create KNO3. Looking at solubility rules, we have all chlorides, bromides, and iodides are soluble except bonded to silver, lead, and mercury. Lead is one of the exceptions, so Pbi2 is insoluble and is a solid. All other compounds will be aqueous, so we write AQ for the state of matter. To balance the equation, we need 2 Ki and 2 KNO3. This is our balanced molecular equation. Next, we can write the complete ionic equation. For the complete ionic equation, all aqueous compounds will be separated into their ions, keeping the equation balanced. Any subscripts we have from crossing charges will become coefficients, and coefficients will be distributed to each element and polyatomic ion in the compounds. If you have multiple coefficients because the subscript also became a coefficient, multiply them together. PbNO₃2 becomes Pb2+ aqueous and 2NO3- aqueous. 2Ki becomes 2K+ aqueous and 2I- aqueous. Pbi2 will remain the same, and then 2KNO3 will become 2K+ aqueous and 2NO3- aqueous. For the net ionic equation, we will cancel out any spectator ions. Spectator ions will be any ions or polyatomic ions that look the same on both sides and do not change states of matter. K+ and NO3- look the same on both sides, so they are our spectator ions, and we will cross them out on both sides. The net ionic equation will be Pb2+ aqueous plus 2I- aqueous creates Pbi2 solid. Determine the limiting reactant and theoretical yield of ZnCl2 when 5 grams of zinc reacts with 5 grams of HCl. The problem mentions a reaction, so we have to first write the balanced chemical equation. When an element and compound react, this is a single replacer reaction, and the element of the same charge as one of the elements in the compound replaces it to make a new compound. Zn has a +2 charge and H has a +1 charge, so Zn will replace H and bond with Cl. Creating the new ionic compound, Zn2+ and Cl- will cross charges to create ZnCl2. H is a diatomic element, so alone, the other product will be H2. To balance, we need 2 HCl. For any single replacement reaction, we should also check the activity series to make sure the element replacing the other in the compound is higher on the activity series. This tells us that the element is more reactive and the reaction can occur. Zn is higher than H2 on the activity series, so the reaction will occur and we can continue. Whenever we are given values for more than one reactant, this is a limiting reactant problem. One of these reactants is going to run out first and limit the reaction. So to find the limiting reactant, the goal is to convert both reactants to the same unit of product. The smaller amount of product found will be the answer, will be called the theoretical yield, and will come from the limiting reactant. The larger product amount found will never be made because the reaction stops at the smaller amount. So just cross it out so it's not confusing. We need to find the theoretical yield of ZnCl2 for the answer so we can convert both reactants to grams of ZnCl2, and the smaller amount made will be the answer and will come from the limiting reactant. For the unit map, to convert 5 grams of Zn to grams of ZnCl2, we will first convert to moles of Zn using the molar mass of Zn, then moles of ZnCl2 using the mole ratio, then grams of ZnCl2 using the molar mass of ZnCl2. The conversion factors will be 65.38 grams of zinc for every 1 mole of zinc, 1 mole of zinc for every 1 mole of zinc chloride, and 136.28 grams of zinc chloride for every 1 mole of zinc chloride. For the unit map to convert 5 grams of HCl to grams of ZnCl2, we will first convert to moles of HCl using the molar mass of HCl, then moles of ZnCl2 using the mole ratio, then grams of ZnCl2 using the molar mass of ZnCl2. The conversion factors will be 36.46 grams of HCl for every 1 mole of HCl, 2 moles of HCl for every 1 mole of ZnCl2, and 136.28 grams of ZnCl2 for every 1 mole of ZnCl2. Setting up all units to cancel, we start with 5 grams of zinc and 5 grams of HCl over 1. In the next fraction, we put the grams for each on the bottom and moles for each on the top. In the next fraction, we put the moles of zinc and HCl on the bottom and moles of ZnCl2 on the top for each. In the next fraction, we put the moles of ZnCl2 on the bottom and 136.28 grams of ZnCl2 on the top for each. We make sure all units cancel out and then we multiply and divide all values. If 5 grams of zinc completely reacted, we would get 10.4 grams of ZnCl2. If 5 grams of HCl completely reacted, we would get 9.34 grams of ZnCl2. We can only make the smaller amount of product, so we never make 10.4 grams of ZnCl2. We only make 9.34 grams of ZnCl2, and HCl is the limiting reactant. Zn will be our excess reactant, and just cross out 10.4 so you don't use it for any answers. How many protons, neutrons, and electrons are in an ion of 35 Cl-? We are given an element, its mass number, and the charge. Mass number is equal to protons plus neutrons, so we can find the number of protons to subtract it from the mass number to get the number of neutrons. From the periodic table, Cl has an atomic number of 17. The atomic number is the number of protons, so Cl has 17 protons. Subtracting the mass number from the number of protons, we get 18 neutrons. To find the number of electrons, we can use the charge equation, charge equals protons minus electrons. -1 equals 17 protons minus electrons, and this will give us 18 electrons. For 35 Cl-, we have 17 protons, 18 neutrons, and 18 electrons. Predict the products and balance the reaction. H₂SO₄ plus NaOH creates blank. We have 2 compounds, so this will be a double replacement reaction. This will also be an acid-base neutralization reaction because H₂SO₄ is an acid and NaOH is a base. An acid-base neutralization reaction will create water and a salt. A salt is just an ionic compound. Writing down the charges for each element, H has a +1 charge, SO4 has a 2- charge, Na has a +1 charge, and OH has a -1 charge. H+ and OH- will bond to create H₂O. Na plus and SO4₂- will bond to create Na₂SO4, and we can now balance the equation. We need 2 NaOH and 2 H₂O. A sample of 25 milliliters, 0.250 molar HCl is titrated with NaOH. What volume of 0.3 molar NaOH is required? For a titration reaction, the moles of acid have to equal the moles of base. We can also use a mole ratio from the balanced chemical equation to make sure they are equivalent. This is an acid-base neutralization reaction, so HCl and NaOH will react to produce H₂O and NaCl. The equation is already balanced. Let's write down the conversion factors we can use from the molarity values given. 0.250 molar HCl will become 0.25 moles of HCl for every 1 liter of HCl. 0.300 molar NaOH will become 0.300 moles of NaOH for every 1 liter of NaOH. We will start with the compound we are given the most information for, HCl. Starting with the single unit 25 milliliters of HCl, we can convert to liters of HCl using a prefix to base unit conversion. We can then convert to moles of HCl using the molarity given for HCl. We can then convert to moles of NaOH using the mole to mole ratio from the equation. We can then convert to liters of NaOH using the molarity given for NaOH, and then we can convert to milliliters of NaOH using a base to prefix unit conversion. The conversion factors will be 1,000 milliliters of HCl for every 1 liter of HCl, 0.250 moles of HCl for every 1 liter of HCl, 1 mole of HCl for every 1 mole of NaOH, 0.3 moles of NaOH for every 1 liter of NaOH, and 1,000 milliliters of NaOH for every 1 liter of NaOH. Setting up all units to cancel, we start with 25 milliliters of HCl over 1. In the next fraction, 1,000 milliliters of HCl goes on the bottom and 1 liter of HCl on the top. In the next fraction, 1 liter of HCl goes on the bottom and 0.250 moles of HCl on the top. In the next fraction, 1 mole of HCl goes on the bottom and 1 mole of NaOH on the top. In the next fraction, 0.3 moles of NaOH goes on the bottom and 1 liter of NaOH on the top. In the next fraction, 1 liter of NaOH goes on the bottom and 1,000 milliliters of NaOH on the top. All units cancel, leaving us with milliliters of NaOH. Multiplying and dividing all values, we get 20.8 milliliters of NaOH. Determine the oxidation number of nitrogen in NO3-1. To find the oxidation number, we can memorize the rules given, but a fast way to remember is to always assign the elements that are on the extremes of the periodic table first. Extremes will mean we assign group 1, group 2, and the more electronegative elements first. Oxygen is more electronegative than nitrogen, so it will most likely keep the same charge it has normally as an ion, unless it's peroxide anion, then it will have a -1 charge. The overall charge of the compound has to equal the sum of all oxidation numbers in the compound. So if oxygen has a -2 charge, the last element, nitrogen, needs a charge, so the total overall will be equal to -1. Setting up an equation to solve for the oxidation number of nitrogen, we can write x plus 3 times -2 equals -1. X will equal 5, and nitrogen has a +5 oxidation number. A student incorrectly predicts a reaction between NaCl and AgNO₃ forms no precipitate. Explain incorrect. When two compounds are mixed together, this will be a double replacement reaction. When a precipitant is mentioned, this is a special type of double replacement reaction called a precipitation reaction. A precipitation reaction will form a precipitate, a solid or insoluble product, based on solubility rules. NaCl and AgNO₃ are our reactants. For a double replacement reaction, first write the charges of each element in the compounds, and then the positively charged ions will bond with the negatively charged ions of the other compound. Na has a +1 charge, Cl has a -1 charge, Ag has a +1 charge, and NO₃ has a -1 charge. The positively charged Na+ will bond with the negatively charged NO₃-. The positively charged Ag+ will bond with the negatively charged Cl-. Crossing charges, Na+ and NO₃- will create NaNO₃, Ag+ and Cl- will create AgCl. Looking at solubility rules, we have all chlorides, bromides, and iodides are soluble except bonded to silver, lead, and mercury. Silver is one of the exceptions, so AgCl is insoluble and is a solid. All other compounds will be aqueous, so we write AQ for the state of matter. We can see that AgCl is a solid, so this will be our correction. Classify each of the following reactions. Two reactants combining to make one product will be a synthesis reaction. H2 and O2 combine to make one product, H2O, so this will be the synthesis reaction. Two compounds reacting to create two new products will be a double replacement reaction. AgNO₃ and NaCl are both compounds, and they are reacting to make two new compounds, so this is a double replacement reaction. One reactant splitting into multiple products will be a decomposition reaction. CaCO₃ is one reactant splitting into multiple products, CaO and CO2, so this is a decomposition reaction. When one element and one compound react, this is a single replacement reaction. Zn is the element and HCl is the compound. Zn is replacing H in the compound to create ZnCl2, a new compound, and now H is alone as a diatomic element, H2. Zn and HCl reacting will be the single replacement reaction. Calculate the number of oxygen atoms in 10 grams of H₂SO₄. Here we do not have a reaction, but we are converting to a new identity, oxygen, an element within the compound H₂SO₄. To convert from the compound to the element, we have to be in moles to use the mole to mole ratio. We count how many oxygens there are in one H₂SO₄ for the mole ratio. We have 4 moles of oxygen for every 1 mole of H₂SO₄. We are given grams to start with, so we need to convert to moles of H₂SO₄ using the molar mass of H₂SO₄, so we can convert to moles of oxygen using the mole ratio, and then atoms of oxygen using Avogadro's number. The molar mass of H₂SO₄ will be 98.08 grams of H₂SO₄ for every 1 mole of H₂SO₄. The mole ratio will be 4 moles of oxygen for every 1 mole of H₂SO₄. Avogadro's number will be 6.022 times 10 to the 23rd atoms of oxygen for every 1 mole of oxygen. Starting with 10 grams of H₂SO₄ over 1, we can set up all units to cancel. In the next fraction, 98.08 grams of H₂SO₄ goes on the bottom, and 1 mole of H₂SO₄ on the top. In the next fraction, 1 mole of H₂SO₄ goes on the bottom, and 4 moles of oxygen on the top. In the next fraction, 1 mole of oxygen goes on the bottom, and 6.022 times 10 to the 23rd atoms of oxygen on the top. All units cancel, and we are left with atoms of oxygen. Multiplying and dividing all values, we get 2.46 times 10 to the 23rd atoms of oxygen. A 0.250 gram sample of CaCO₃ is decomposed. What mass of CO2 is produced? This decomposition reaction will be a special type with a metal carbonate. When a metal carbonate decomposes, it produces a metal oxide and carbon dioxide. The metal oxide for this reaction will use the metal given Ca with its charge +2 and oxygen with its charge 2-. Crossing charges, we get CaO when the 2's cancel out. The reaction will be CaCO₃ produces CaO and CO2. The equation is balanced, so we can now set up our unit map. We are given grams of CaCO₃ and need to convert to grams of CO2. We have to convert to a new compound, so we need moles of CaCO₃ to be able to use the mole ratio from the equation to convert to moles of CO2. Afterwards, we can convert to grams of CO2. To convert from grams of CaCO₃ to moles of CaCO₃, we use the molar mass of CaCO₃. To convert from moles of CO2 to grams of CO2, we use the molar mass of CO2. The molar mass of CaCO₃ will be 100.09 grams of CaCO₃ for every 1 mole of CaCO₃. The mole ratio will be 1 mole of CaCO₃ for every 1 mole of CO2. The molar mass of CO2 will be 44.01 grams of CO2 for every 1 mole of CO2. Setting up all units to cancel, we start with 0.250 grams of CaCO₃ over 1. In the next fraction, 100.09 grams of CaCO₃ goes on the bottom, and 1 mole of CaCO₃ on the top. In the next fraction, 1 mole of CaCO₃ goes on the bottom, and 1 mole of CO2 on the top. In the next fraction, 1 mole of CO2 goes on the bottom, and 44.01 grams of CO2 on the top. All units cancel, and we are left with grams of CO2. Multiplying and dividing all values, we get 0.110 grams of CO2. How many grams of solute are needed to make 500 milliliters of 0.2 molar aluminum nitrate? Here, our solute will be AlNO₃. We are going to start with 500 milliliters of solution and convert to grams of aluminum nitrate. We can use the molarity conversion factor if we have liters. So we can convert milliliters to liters using a prefix to base unit conversion, then convert to moles using the molarity value, and then convert to grams using the molar mass of aluminum nitrate. There are 1,000 milliliters of solution for every 1 liter of solution, 0.2 moles of AlNO₃ for every 1 liter of solution, and 213.01 grams of aluminum nitrate for every 1 mole of aluminum nitrate. Setting up all units to cancel, we start with 500 milliliters of solution over 1. In the next fraction, 1,000 milliliters of solution goes on the bottom, and 1 liter of solution on the top. In the next fraction, 1 liter of solution goes on the bottom, and 0.2 moles of aluminum nitrate on the top. In the next fraction, 1 mole of aluminum nitrate goes on the bottom, and 213.01 grams of aluminum nitrate on the top. All units cancel, and we are left with grams of aluminum nitrate. Multiplying and dividing all values, we get 21.3 grams of aluminum nitrate. I hope these study questions helped you review for your exam. Good luck on your exam. You've got this, and keep practicing.